is there already. Yep, I believe so. Yep, hmm? I think so. I can check right now. So last Wednesday, you said? Okay, maybe it's not public yet. Because all of these will go into unlisted first, and then they will go public. Okay, so what day am I talking about? Oh, you're right. Okay, you're right. Okay, so the third has not been released yet. I'm gonna release it now. Okay, 0403. Okay, there we go. It should be public now. Yep. Thank you. Well, thank you for reminding me. All right. So what we'll do today is to look at time complexity, and let me change the resolution of the screen first because right now it's not displaying everything that I'm seeing on my laptop. So let me just change it to so that we have the same resolution on the projector. I'm writing a script. I'm going to write a script so that, by hooking up to a specific monitor, the script will automatically resume, whatever resolution it was using. Um, but, it will take time to get it done. So it's being done. All right. So what we'll do today is to look at the actual time complexity of certain algorithms that you probably know already. So the algorithm itself should not be a big problem. It is really just, how do we understand or analyze the time complexity of the algorithm. So that's the part that we're going to be focusing on. The first one is linear search. So when we talk about linear search, this is the algorithm, okay, and this is the recursive one as an algorithm. So what we need to do is to look at which part is recursive, right? So there's only one recursive part, which is here. And then we have to look at the rest of the algorithm and try to figure out what does the rest of the algorithm depend on the size of the problem, okay? What do you think? Okay, let's just go line by line. Look at line 7. Does line 7, with one particular instance or one particular invocation of the subroutine, does line 7 depend on the number of elements of A as an array? Nope, it's a constant time thing, right? What about line 8? It's a comparison of B versus the number of elements in A, which is an array. So would that take constant time, or would it depend on the length of the array A? It's constant time for an array, but if it's a linked list, then it would depend on the actual length of the list. It depends on the implementation of the list, because if you keep track of the number of items at the head of the list, it can still be constant time. But if you have the simplest singly linked list, then you have to traverse all the way to the last element to find out how many elements there are in the list. But in this case, because we are dealing with specifically an array, then it's constant time. So now we look at line 9. Okay, if you look at line 9, not counting the recursive call, this part here, okay, which is just the assignment, which is constant time, and we are comparing a particular element to the value of v, that's constant time as well. So what this is telling us is, other than the recursive call itself, the rest of the algorithm takes constant time. Are we okay with that concept? Okay. So when we look at the time function, okay, we go back to the time function here, it can be expressed like this now, where t of n is the actual amount of time for the algorithm to complete when an array has n elements. Is that okay? And then k1 would be the combined amount of time for all of those constant time operations that I just mentioned. Okay? And then t of n minus 1 is how much time the recursive call itself is going to take. But wait, why is it n minus 1? So if you go back to the algorithm and you look at how we perform the recursive call, you will see that the recursive call is using the same array A, but the index is no longer B, it is B plus 1. So the remaining number of elements that I need to examine with this recursive call is now one fewer than the current instance or the current invocation. So that is why, when we look at the recursive call, the time complexity is not T of n, it is T of n minus 1. Is that okay? All right, cool. So any algorithm that looks like this has a type bound which we represent using big theta as n. So in this case, T of n is an element of big theta of n, which basically means n is a type bound of T of n. It is growing linearly with the size of the problem. Do we have any questions about this analysis of a linear search algorithm? No questions? So we're all good here? Yeah, go ahead. Uh-huh. It basically compares element B of array A with V. I mean, because I'm using pseudocode, so a single equal means actual comparison. So this is either true or false. This is a logical OR, and this is the recursive call.
So all of it is being stored in the whole thing, both sides of the disjunction.
Both of this. So the entire disjunction is stored in R, which is only used here so that I don't return inside a conditional statement. Is that okay? All right, cool. All right, so if we're good with this one, the next category of algorithms we'll be looking at would be selection sort, bubble sort, insertion sort, and so on. They're kind of all lumped into one category because they all share a particular common attribute. So what we'll do is we're looking into selection sort. This is the pseudocode of selection sort. We'll just take a quick look at it and figure out how it works. We are given an array A, okay, by reference, because with any type of sorting algorithm, you probably want to do an in-place sort if it is possible. And then we have a by value B, which changes when we perform recursive calls. So the first thing is, under what condition do we have nothing to do? Well, we can see that the then branch is when we do have something to do. So the else branch, which is not listed here because there's nothing to do, is when the recursion can end. So can someone tell me when do I have nothing to do with a particular invocation? When bar A bar minus 1 is less than or equal to B. Okay? Which means B, which is an index supposedly into the array, is already beyond the index of the last element of the array. Okay? So what B is doing is B is basically saying, this is the one element I'm focusing on, and I need to make sure that the correct element is at this position. Okay? So with each invocation of this particular selection sort algorithm, all we are doing is to say, okay, I'm only in charge of making sure that this element, okay, at index B is the correct one. I don't really care about the rest. Is that okay? So that's the general idea of selection sort as a recursive algorithm. Okay, so given that B is the index of the element that I want to make sure is at the right place, how do I make sure that happens? So this is the rest of the algorithm. It looks really long and complex, but when you look at line 5 all the way to line 14, all we are trying to do is to make sure that we find the smallest element from index B to the end of the array. Okay, so let's check out the algorithm. Let's try to check out the algorithm line by line. 5 and 6 are just declaration of the local variables. So what M is M is storing the index of the, I think we are doing smallest or largest. If it's smaller, we update. So we are keeping track of the smallest, okay? So M is the index of the smallest element from B and on, index B and on. So we are looking at index B plus 1, index B plus 2, all the way to bar A bar minus 1. And we're trying to find out, okay, which element has the smallest value. But we don't want to store the value of that. We want to store the index of the element. I, on the other hand, is just really moving along. I is just I is an index variable, so that we can say, okay, which one are we examining now? Okay, so I is just sequentially incrementing. So we initialize M to B because we just make the assumption and just say that, well, let's just say that B is the one having the smallest value, for the rest of the array. Now, of course, that assumption is usually wrong, but we'll fix it as we encounter elements that are actually smaller. Is that concept okay? All right. Then we can use B plus 1 to initialize I. Now, if you use B to initialize I, the algorithm will still be correct. It's not a problem. But you just waste one entire iteration because you'll be comparing A bracket M to, you'll be comparing A bracket B with A bracket B for the first iteration, which is not needed, okay? So that's why I initialize I to B plus 1 to basically say we are already assuming the element at index B is the smallest. Let's check the rest of the array. That's basically what the plus 1 is doing. So from line 9 to line 14 is a loop to basically go through all the elements from index B plus 1 all the way to the end so that we can try to find the smallest element in that portion of the array. So as long as I is less than bar A, which means I is still a valid index into the array, what we do is we compare A bracket I, the element I of A, with element M of A. If element I of A is less than element M of A, that means, what we thought was the smallest is not the smallest. We just found something smaller than that. So let's go ahead and update the index of the smallest element of the array, and that's all we need to do. Is that okay? And then we move on, after the conditional statement, we just increment I so that we can move on and look at the next element of the array. Is that okay? All right, so looking at this part of the algorithm, and then we have the swap operation. I'm not even going to spell out, how we exchange the values of two integers because you guys know that already. And then we do a recursive call on line 16, which has the same element, which has the same argument A, but the index of the element that the next invocation has to deal with is now B plus 1, because the element of that B is already taken care of. Is that okay? So the algorithm is relatively simple, but what we want to do is to calculate the time complexity. Is that okay? So now, if you look at the time complexity, how much time do you think line 4 is going to take to compute? Constant time, because it's an array. Line 7, constant time. Line 8, constant time. And then from line 9 to line 13, we're dealing with a loop. So now the question is, how many iterations do we have to go through with this loop? It's going to be bar A bar minus B, because we're starting with B plus 1. So yeah, so bar A bar minus B is how much time it takes, because we're only looking at the remaining elements, right? Okay. What about line 15? Line 15 is a recursive call. So if the amount of time to handle the current invocation is T of bar A bar, T of B, then the next one is going to be no, take it back. If the current time complexity is T of bar A bar minus B, then the next invocation is going to take T of bar A bar minus B, and then the whole thing minus 1, because it has one fewer element to consider in the next iteration. So when you look at the time complexity T of n, this one is going to be expressed like this. we have the K1 component to take care of everything that is constant time. Okay, like the assignment, the initialization of the index variable, the initialization of the index of the smallest element, all of those, and also the returning of the result, the swap operation, those things all add up to K1, basically just the constant time component. The second one is K2 times n, because we have to go through the loop n times, assuming that we have n elements left to take care of in the current invocation. So that's why we have K2 times n. Now, the exact value of K1 and K2 really do not matter, okay, because we have a larger component to take care of next. And then we have the recursive call. The recursive call has one fewer element to take care of, so the time complexity of the recursive call is t of n minus 1, because we took care of one element in the current invocation, so the next invocation has one fewer element to take care of. So are we still doing okay with this equation here? Yep.
So like the minus part for how many times you go through the loop, that's going to end up making a difference as you go deeper into Tn minus 1, Tn minus 2?
Yeah, so eventually it becomes t of 0, where it's just constant time, and then it starts to return.
What I'm asking is that where that will show up, is that going to be the thing next to K2? So you'd have like in Tn minus 1, you'd have n minus 1 times K2, and so on and so forth as you go and expand it out?
Yep, you can expand it out like that. Yep.
Okay.
So if you look at this recurring relationship, you can just expand out everything. So when you expand out everything, we get to something that we are familiar with. Okay, if you get rid of the components that are growing smaller, so for estimation purposes, we only have one component left, which is something like this. Because when you expand it out, okay, let's go ahead and expand it out and see what it looks like. So if you expand this out, then you end up with K1 times n, okay, after you expand everything. We assume that t of 0 is just a constant time, or constant time. And then because in the current invocation is n, K2 times n, the next invocation is going to be K2 times n minus 1, and then the one after that is K2 times n minus 2, and so on. So when you expand out the entire thing, then you have K2 times, in parentheses, n plus n minus 1 plus n minus 2 all the way down to 0, okay? And the last component goes away because we are expanding it, right? So after expansion, t of n minus 1 is no longer there. So after expansion, it is going to look like, I probably skipped that derivation. But after the derivation, it would become something like this, which first time we encountered this was when we talked about the g function, because we talked about what is the closed form of 1 plus 2 all the way to k, and that's basically what we have here. And the base case is when we are dealing with t of 1. So when we're dealing with t of 1, we just get k. And then this is proved by induction. So to deal with t of j plus 1, we end up with this, which is the same as what the theorem is saying. The theorem is this part here. This is the theorem. This is the case when n equals to j plus 1. Okay. So now that we know that t of n is k times n plus 1, the whole thing divided by 2, then we can show that t of n is an element of big O of n squared, which basically means, okay, can someone tell me what big O means? If I say, t of n is an element of big O of n squared, what is that really saying? It's an upper bound. Very good. Yep. So n squared is an upper bound of t of n. But we also know that t of n is an element of big omega of n squared. What is big omega? The lower bound. Okay. So because n squared is both the upper bound and the lower bound, then it becomes the tight bound, which is big theta. Now t of n does not oscillate. It does not go between two values indefinitely. So we can just take the limit. So when you take the limit of t of n divided by n squared, so n squared, once again, is the estimate function. T of n is the actual function. So when you do the multiplication, when you work out the actual value, then we can separate the k divided by 2 outside, and then we have n times n plus 1, the whole thing divided by n squared, still being dealt with by the limit. So when you go through this, then we have n squared plus n. N squared divided by n squared is just 1. Okay, so that eventually just becomes k divided by 2. But n divided by n squared is simplified to n 1 divided by n. When n is going to infinity, the limit becomes 0. Is that okay? So now we're just adding k divided by 2 by k divided by 2 times 0, which is just k divided by 2. So what is so significant about k divided by 2? If you remember the discussion of the big O and the big omega notation, one thing we know about k divided by 2 is it is greater than 0, and it is also less than infinity. And because of that, we now know that t of n is an element of big theta of n squared, because that's one way to define what is the big theta of a particular function, time function. So are we doing okay so far with this? Because this stuff still relates back to the big O, big theta, and big omega notation discussion, and also the concept of limits. Is that okay? Okay, so I know this stuff is kind of heavy, so let's go ahead and look at something a little bit lighter, okay? So I'm going to give you, I'll present this question in a spreadsheet here. Not spreadsheet, but mousepad. There we go. So if I say, I'm taking the limit where I goes to infinity, and we are talking about the summation of I, okay? So we're talking about 1 plus 2 plus 3 plus blah, 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 I. What do you think is the value of that limit? You go like, well, that's going to be, it's going to be infinity, right? Okay. But if you watch on YouTube, that is not the case. It's misinterpretation of some terms, okay? So we'll say 3, and it is 1 divided by 1/12 of something. There we go. I'm not going to run through the whole video because there's no need to do it. And the speaker is not working either. But if you're interested, you can actually just watch it yourself. Yep.
Doesn't this theorem make like a lot of math assumptions that aren't correct though?
That is correct. That's why they arrived to that conclusion. That cannot possibly be the case, right? So when you look through the whole video, you can kind of go through this exercise and figure out which part is the where's the fallacy of this argument. Okay, let me just kind of go to the frame that I want to. It's negative 1/12. So using incorrect arguments, incorrect application of logic, this guy and a few other people can come to the quote-unquote conclusion that if you add up 1 plus 2 plus 3 all the way to infinity, the value is negative 1/12. But this is a good example for you guys to go through, because if you can spot where the assumptions were wrong, okay, where the logic was applied incorrectly, where they did not use the correct definition of certain symbols, then you're doing good. Even if you cannot spot those problems, just understanding that this just doesn't look right, is good too. I mean, does it look right to you that we are adding a whole bunch of non-negative values, and then the sum is negative 1/12? Yeah, so you have to watch this. I was introduced to this video by Larry Dumas, and he just spotted this video for whatever reason, and I don't think so. It's this is misleading, right? It's a very good. It's very deceptive the way they did it. Okay, so it's kind of like a magician, except you're not watching a magic trick. You're basically watching an invalid derivation in mathematics, but is nonetheless actually not correct. So if you're since we're talking about summation and to infinity, this is one video that you might want to watch. It's kind of interesting. And the URL is here, so when you watch this video again, you can just copy the URL. Huh? Let's see. This is okay. This is the right slides. We're just at a different place. There we go. Okay. So as it turns out, we can make more statements than this. If the time function of a recursive algorithm can be expressed like this, k1 plus k2 times n plus t of n minus 1, then anything that has this type of description for the time function has a big theta of n squared. It belongs to big theta of n squared. So as it turns out, if you look at bubble sort, it has the same kind of structure in terms of time complexity. We just work with selection sort, but insertion sort also is the same thing. Okay. So do we have any questions about this discussion here? No questions? All right. So if this is okay, we'll look at yet another type of recursive algorithm. This time is binary search. Okay. So with binary search, and we explore that in this module, so it has a link to the other one. So we looked up binary search, and this is the binary search algorithm. So the first thing we do is, when we are analyzing for time complexity, we are basically looking at, which portion of the algorithm is constant time, and which portion is the recursive call, and which portion is not constant time. So not counting the declaration, which is up to line 7, let's go to line 8. How much time do we need to compare two integers? B is an integer, it's just an index. E is an integer because it's also just an index. That's constant time, okay? And then, of course, we're usually not that lucky that we return false right away. So we'll go to else, and then we have to compute m, which is the midpoint index. B plus E divided by 2, take the floor of that, and then use that to change m. That's constant time, okay? Line 12, constant time, because A is an array. Line 14, constant time as well. And then line 16, constant time. But you have to be careful, because you have to know whether there's a potential to recursively call binary search on line 13 and also on line 15. That makes a big difference. Now, in this case, we are not going to call both in the same invocation, because they belong to different branches of a conditional statement. So you will only take either line 13, line 15, or if you're super lucky, line 17. Okay? So now you look at the recursive call. The important part of the recursive call is what is the size of the problem when you perform the recursive call. That is the key issue here. In all the previous one, okay, in the recursive call, the problem size is only decreased by 1. In this one, it is not reduced by 1. How is it reduced? The size of the problem is the difference between the second and the third argument. So how is it reduced in this case? It's cut in half, okay? So when you perform the recursive call, the problem size is halved, okay? Okay, so with that in mind, going back to the slide that we came from earlier, the time complex or the time function can now be described using this particular equation. The amount of time to solve the case when the problem size is n is k1, which is the combination of all the constant time operations, plus the time function of the recursive call. But the recursive call is dealing with a problem where the size is only 1/2 of what we're dealing with the current one. So the problem size is just n divided by 2 in this case. So as it turns out, in this case, any algorithm that has a pattern that looks like this, where r is less than 1, the time complexity has a big theta of log of n. In other words, r is the reduction factor. And I think this is not supposed to be x, this is supposed to be r. I don't know why it is still unfixed here, because I thought I fixed it. Let me just do a Control R to refresh it. Oh, Control R, not Shift R. There we go. It's still not fixed. Okay, fine, we'll fix it. This is a very early module, 0090. It's really early. Do you guys know why it is that early? Because there was one semester I had to, they gave me one weekend to prepare myself to teach 400, 430, and 440 in that semester. In other words, the Friday before the entire semester starts, the dean came to me and go like, Tech, would you be interested to teach? No, this is already done. Okay, maybe I just haven't rerun the update one. So anyway, so it was the Friday before the whole semester started. The dean came to me and asked, so Tech, do you want to take on 400, 430, and 440? Because Professor Fox in that particular semester became interim dean. So he would be 100% interim dean and would have no time to teach his usual classes. And the note was written in that particular semester. So I was frantically prepping myself for 3 new preps because I had never taught 400, 430, nor 440 before. So all of those were new preps to me in that semester. And guess what? That semester was also the semester where I was getting performance evaluation, which worked out to my advantage, because I can now have something to blame on. But I did all this stuff here. I did all the notes for 400, 430, and 440. Getting back here. Okay, do another refresh. And binary search is down here. Yep, okay, so there we go. So now we're good. So R is a reduction factor. So R, as long as R is less than 1, it is still big theta of log n. It's just a different constant that you're changing. So what that is saying is, what if the reduction factor is only 2/3? It's not quite a half. It's still big theta of log n. What if this reduction factor is better than 1/2? What if it's a quarter? It is still big theta of log n. So do we have any questions about binary search? I mean, is this surprising to you that binary search has a big theta of log n? Nope. Because if you are taking 430 in this semester, have they started to talk about trees yet? Yeah. Okay. But the moment you start to talk about trees, okay, then you start to understand, oh, with any type of trees, the total number of nodes, including all the leaves, is the exponent of the number of levels, assuming you have the constant fan out from each node. Is that okay? So you can reverse the psychology or reverse the reasoning and go backwards and say, oh, if we're doing binary search, we're going here, here, and here, and here. But that is just reversing the whole reasoning and go like, oh, okay, if we have this many leaf nodes, okay, how many levels can lead to this many leaf nodes? So you can kind of intuitively use that line of reasoning. The last one is merge sort. Merge sort is a very interesting one. So let me just kind of, you like that one? So merge sort is one of the many algorithms many of the sorting algorithms that has a time complexity of big theta of n log n, okay, which is the best you can do. In this class, I'm not going to talk about why you cannot find a faster algorithm to do sorting. In the upper division of this class at a 4-year university, then you will actually know the logic behind that argument, where you cannot find a faster algorithm to sort an array. N log n is the fastest you can get. Now you can change the constant, okay? If you compare merge sort to other efficient sorting algorithms, the constant would not be the same. But you're not changing the function itself or the shape of the function. So we proved this in module 0079, that the iterative version of merge sort, and we'll prove this. We also proved this in module 0087 for the recursive version of quicksort. So let's go back to here. Okay, go to 0079 and look at non-recursive merge sort. So with non-recursive merge sort, the first step is to split. Okay, the best way, I mean, you can read all this stuff here, but the best way for me to do is to illustrate the whole process, okay, by hand. So let's do it by hand a few times. Once should be enough to kind of convince you that it works. So like with most sorting algorithms, the worst case is when you give it something that is sorted but in a reverse order. That usually will give you the worst, the worst case. So if I want the array to be sorted in a non-decreasing order, the worst case is the input is exactly the opposite. Okay, so we'll give it exactly the opposite. So we'll have 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, so we have exactly 16 items in the array, and they are sorted in opposite direction of what I want, because I want it to be in non-decreasing order. Are we good so far? So what merge sort does is, the first thing it does is to split. Now split means I have one input and I have two output arrays or tapes or linked list or whatever you want. Okay, it doesn't have to work with arrays. The time complexity of merge sort does not rely on the use of an array. You can use a tape, you can use a singly linked list, and it still maintains the same time complexity, which is great because many of the other sorting algorithms rely on the fact that you're using arrays. If you do quicksort, for instance, and you say, oh, but sorry, I'm using quicksort, but not on an array, I'm using a linked list with quicksort, then the time complexity doesn't look so hot anymore. Okay? But merge sort is one of those kind of strange algorithms where you can use a singly linked list, or you can even use a magnetic tape, okay, where random position access is really, really slow. It will still maintain that n log n time complexity. Okay, so the first split, okay, split is to basically say, I'll put 15 first. Okay, I look at 15. And if the next element is in order, we'll keep that run, okay? So is 14 in order with that 15? No. Nope. So I would put 14 into the next tape, okay? Well, I'll maintain two tapes alternately, okay? Then we go back to the first one and ask, oh, excuse me, we cannot switch back yet, because now we have to look at what is after 14 in the original series and ask, is 13 naturally following 14? Nope. Okay, so now we have to put it back to the first one. Okay, and then 12 does not follow 13, so it has to be here. 11 is here, 10 is here. You can kind of tell what it's doing, right? And it doesn't seem to be doing anything useful at all. So we got 9, 8, 7, 6. Okay, I'm going to get rid of that line here. 5, 4, 3, 2, 1, 0. Now, someone can say, but Tech, you could have just put all the odd numbers on one line and then put all the even numbers on the other line. Yes, I could have done that. But the order that I update these reflects the actual order of the merge sort algorithm. So what you do is you can kind of imagine that the original sequence of numbers as one tape of a mainframe computer, and you have two tapes as the output of this particular process. Okay? Did I have to go back and forth on these tapes, on all three tapes? Nope. On the input tape, all I'm doing is I'm just scanning through like this, and I only need to keep track of 2 records at any particular time because I need to know, am I looking at something that is already in sequence, or am I looking at something that's out of sequence? And I just need to maintain 2 items in memory in order to make that determination. Okay? What about the output? I'm not random accessing the output either. I'm just appending each step. Is that okay? Okay. So what do we do now? We merge. Okay. So with the merge process, it goes like this. Okay. We started with a 15, and then we ask, okay, is the next thing of 15 in order in this case? And the answer is no, it's not. Okay. But, oh, wait, I take it back. So we rewind the tapes to the beginning, but this time we are reading these 2 arrays instead of writing the 2 arrays. So now we have to maintain indexes. So we have to now say, with 1, we are looking at this item. With the other one, we are looking at this item here. And then we ask, which one is the smaller one? Well, the 14 is the smaller one, okay? So when we merge, we take the smaller one. And then once we take the smaller one, we have to advance its tape head to the next one. So now we compare the 15 and the 12. Which one will keep the run going? No, 12 won't keep the run going because I want things to be in order. It's the 15. So if I cannot keep the run going, I will find the one that is the smallest. If I can keep the run going, I will pick the one that keeps the run going. So when I say a run, it means a run of a sequence of values that are in the correct order. Okay. So because I'm using the 15, I have to move the tape head to here now. So now I have these 2 to choose from. Neither is going to continue the run, okay? Because neither is greater than or equal to 15. But now I choose the smaller one to start the next run, okay? So you have several conditions to evaluate. If you're starting a new run, you choose the smaller value to start a new run. Otherwise, you continue the run as much as you can. Okay, so the 12 is now used, and then we move on to the 10, and now we compare which one we should use. If I choose a 10, I break the run. If I choose the 13, I continue the run, so I choose the 13. So now we look at these 2. Both of these will break the run. There's no way for me to continue the run at this point, so I choose the smaller value to start the next run, which in this case is 10. And I'm not going to go through this because it takes a lot of time to update the cursors, but you can kind of see that the output of this is going to be 10, 11, and then it will be 8, 9, then it will be 6, 7, and then 4, 5, and then we have 2, 3, and then 0, 1. Is that okay? But what are we seeing here? Now instead of, it's still real terrible, right? It's still terribly out of order. But we can see that there are only 8 runs, as opposed to the original, which has 16 runs. 16 runs, each run only has 1 element. Now we have 8 runs, each run has 2 elements. Is that okay? So the next step is to look at this, line 16 as the input tape, and then we will split it again into two tapes. So we'll do the same thing. We say 14, and can I continue this run? Yes. Okay. So 15, and after this we have the 12. Can 12 continue this run? Nope. Put it onto the alternate tape. We're looking at 13 now. Can 13 continue the tape? Yes. So we do you see what we are doing here? So after this we have 10, 11, and then we have 8, 9, and then we have 6, 7, 4, 5, and then we have 2, 3, and then we got 0, 1. Are we doing okay? Fine. Should have used a spreadsheet to do this. Okay, so now we merge again. Same deal. We look at 12 and 14 as the head of the whole thing. And we go like, well, we're starting a new run, so we should pick the smaller value to start a new run. So we're going to choose 12. Okay. Once we have chosen 12, then the bottom one would move on to 13. The top one is still at 14. So now we choose and go like, well, they can both continue the run, but one is smaller. We'll choose the smaller one to maximize the chance of maximizing that run. So now we choose the 13. Now we are looking at 14 versus 8. The 8 is going to break the run, but the 14 actually continues the run. So this time we'll choose the 14 because it continues the run. And now we are up to 15 and 8. So 15 is the choice. Okay. Now we are to the point where we have to choose between the 8 and the 10, because it's going to break the run anyway. Okay. The 8 is smaller, so we choose the 8. And then we have the 9 versus the 10. We choose the 9 because both are continuing the run, but 9 is smaller. And now we are looking at 4 versus 10. 4 is going to break the run, but 10 continues the run. And then we are choosing between 4 and 11. 11 continues the run. 4 does not continue the run. So now we are getting to comparing the 4 versus the 6. Once again, we choose the smaller one. And then now we are choosing between the 5 and the 6. 5 is the smaller one and continues the run. And now we are choosing between 6 and 0. We choose the 6 because the 0 breaks the run. And then we are now choosing between the 7 and the 0. 7 continues the run. So now we're getting to comparing the 2 and the 0. 0 is the smaller one, so we use it to start the run. 1 is smaller than 2. And then 1 tape is already done, so we have no choice but to copy the other tape over. Okay, but you can kind of see the log n portion now, right? Because each time we do the split merge, the run gets twice in terms of size. But you should be counting the number of runs. Okay, the number of runs after each split merge iteration is halved. So now we can, you can pretty much figure out how this is going to work out, because now we have 12, 13, 14, 15 on one tape, because this is one continuous run, and then we have 8, 9, 10, 11 on the other one, and then we get to 4, 5, 6, 7, and then here we have 0, 1, 2, 3. So after another merge, then we have 8, 9, 12, 8, 9, 10, 11, 12, 13, 14, 15 as one run. And then we have 0, 1, 2, 3, 4, 5, 6, 7 as the other run. Then we split again. So now it's easy because one tape has 1/2 of all the numbers. The other tape has the other half. Okay. And then when we merge again, then we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. How many iterations did we go through? I consider one iteration consisting of a split and a merge. 4 iterations, because 2 to the power of 4 is 16. So we only need 4 iterations to do it. Now, what is really, really cool about merge sort is not only the fact that it works on tapes, okay? Now, I think as as time goes on, it is more and more difficult for you guys to understand what kind of tape we're talking about. So this is what kind of tape we're talking about. I mean, when was the last time you saw a computer that runs on these tapes, reels of tape, to store data? In a museum. Okay, thank you. That's about right. So merge sort works exceptionally well with tape reels. You just need 3 of them. And it takes minimal amount of RAM to work because you only need RAM to store 2 records. But you can be sorting like billions of records with only a tiny amount of memory. Sorry?
You want to study medicine in the Caribbean?
Study, oh, study medicine in the Caribbean. Is that on a cruise ship? Cruise ship as a campus. Now that would be kind of an interesting concept. Let's click it, right? All right. So this is IBM 720 vacuum column tape drive. Oh, it actually works too. Nice. Okay, so you might look at this and go like, okay, but how does this relate to me? Because we are not using tape drives anymore. So how does it relate to me? Okay, what is the memory type? So let's say you have a motherboard and you have a computer and you want to upgrade your memory. So when you go buy your memory, what are some of the things that you need to know? Part of the specification of RAM. Huh? Type of processor, which dictates the type of RAM you can use. So some of the older processors would use DDR3, and the newer processors, they all make use of DDR4. Is there DDR5? No. So DDR4 is the most recent consumer grade memory module. So can someone tell me what is DDR and how it works? Data rate. Well, that's the original one, double data rate. But now we are not just doubling. We are actually doing a lot more than just doubling. But what it does is it can do very efficient burst mode read and write access. Okay, so basically the way it works is the processor will talk to the memory module and say, okay, let's agree on a burst transfer after this. Okay. So and then the processor will tell the RAM module and say, we're going to start with this location. The RAM says, okay, and let's start, okay? And the way it works is they each keep track of time separately. It is not synchronous anymore, it is asynchronous. So for each clock, okay, you remember your RAM has its own clock, which is usually running at hundreds of megahertz, right? So for each clock edge, okay, it's just like a metronome. Okay, the metronome goes like tick, and the metronome can be heard from both sides. Okay, so it's tick, 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 like that. But the actual transfer is not transfer, 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 transfer. It's more like, tick, transfer, transfer, another tick, transfer, and then between the ticks you have another transfer. So if your base bit is like, then the transfer goes like that. So that's why it's transferring so fast, because it is not resynchronizing with anything. You don't need to tell it, oh, this is the next location and this is the data of the next location. The RAM module itself has a counter to keep track of where the next location is. So all the processor has to do is to keep pumping into the data bus, and then the memory module itself knows based on timing. okay, when to capture the data bus and what locations are supposed to be getting that content. So the difference between all the variations of DDR is how many beats or how many transfers you're fitting between the actual ticks of the clock. And also what is the size or what is the length of each burst transfer. Is that okay? So how is that going to help your computer go faster? What assumption is it making? And say, well, this is going to make your computer go faster, assuming blah, 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 blah. What is that blah, 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 blah? Yep. The processor is faster than RAM, and it is also executing or accessing data sequentially. Okay? If your program is written in a way that it accesses locations all over the place, there's no sequence, okay? Then each burst transfer is only good for actually one location. Okay? And then you have to use another burst transfer for another location, another burst transfer yet another location. So now it's useless, okay? You have just defeated the whole purpose of DDR4. But DDR4 is exceptionally efficient when you say, oh, I'm just going through this array sequentially. Because that burst transfer, you're going to use up everything that was burst transferred before the next burst transfer. So now you're utilizing the full efficiency that your computer architecture is supporting. Is that making any sense? Okay? But how does that relate to the tape of a mainframe computer? Or merge sort? So let's go back to this here. When we perform merge sort, we are sequentially reading, we're sequentially writing, which means the mechanism of burst transfer can be fully utilized. If you're doing quick sort and you look at what elements are getting updated using quick sort, it's not sequential. It's all over the place. But this is very sequential. So what it means is if you implement merge sort and you implement quick sort using arrays and on the same architecture, the merge sort method is probably going to be faster than the quick sort method because it is fully utilizing the underlying mechanism of a modern computer that allows you to access sequential locations with very, very high efficiency. Next question. Where is it storing all that burst transferred material? Because you're burst reading RAM or you're burst writing to RAM. So if your burst reading is reading in, okay, I'm just giving a guess here, it's reading in 512 bytes. But your processor doesn't have 512 bytes internally to store anything. It has got a few registers, and that's it. So where do you think those 512 bytes are located after you perform a burst read? It starts with the C. Cache, exactly. So that's where cache comes in handy, because when you're burst reading from RAM, all that stuff is stored locally into the cache, right, which is on the same die as your processor. So as your processor continues to fetch the next instruction, or is going from one element of the array to the next one, it asks for, oh, give me the next location. It is at this address. Now your memory bus doesn't have to go all the way to the memory modules. It can just go to the cache and go like, yep, I got a local copy because of the burst transfer earlier. So all of these concepts, kind of tie in when you study computer architecture and this class, computer algorithm, analysis and stuff like that. They're all related. I just wanted to kind of point out that. We got 5 minutes left, so I'm not gonna do any further analysis here, but I do have one more thing to do. Okay, I'm not gonna let you guys go 5 minutes early. That never happens. Okay, so how many people have heard of mainframe programming? So since we just looked at the mainframe picture, might as well just point out, go back to that slide. So how many of you want to do programming with mainframes? No one. Okay, one person. Okay. But this is not our current mainframe anymore. Okay, so if you look up IBM mainframes or IBM Z mainframe and look up some images, that's what mainframes look like now. They look like a stealth fighter, right? I mean, and they're super duper in terms of processing power. Inside these closets, you won't find tapes anymore. So in fact, the IBM mainframes, probably pack more processing power per square, per cubic, whatever you want to measure, compared to the other alternatives. So this is what mainframe is about now. Next question: why do you want to consider your programming in mainframes? Who's using mainframe? The government. So the Department of Technology, which is kind of the AWS of the state government itself. Okay, so they supply platforms to other departments. They are all mainframe based. Next question: why do I want to consider mainframe programming when I can just go to the Silicon Valley and work with JavaScript and AWS or Google App Engine and all the other cool stuff? And mainframe is so obscure. Why do I want to consider getting a career, starting my career with mainframe computing instead of the other types of computing that is really hot right now in the Bay Area? What do you think? Huh? Well, in terms of money, the Bay Area has more money. I mean, if you get hired by one of the startup companies in the Bay Area, your monthly salary is more likely to be higher compared to a government employee. But what is the difference? Well, retirement. So this argument does not apply to anyone who do not plan to live past 40 years old. So those people can work in the Bay Area. Okay, there's nothing about working the government that's going to be beneficial if people are planning not to live past 40 or 50. But for people who do plan to live up to like 70, 80, and want to have a retirement that has a secure income, government jobs is not bad. Okay, so look up the pension plan of the state government, okay, and see how they calculate your monthly pension check after you retire. It is actually predictable. In other words, you can plug in formulas and equations and numbers now, today, and know that, oh, when I retire at 65, my monthly pension paycheck is going to be at least this much. Huh? Well, it depends on how long you work, right? I mean, because it has to do with time of service, like duration of service, and your age of retirement, and many other factors. But CalSTRS has a calculator to do all that. But there's one more factor: how easy it is for you to get a job in the Bay Area as opposed to getting a job with the state government. That's a very tricky question. Okay, this is the trickiest question of the entire discussion. Because most people think it's easier to get a job in the Bay Area because right now they're hiring everybody who can write code. Okay? But with the government, all of those people who used to write code on those mainframe computers that actually had tapes, those programs are still being used today. But most of those people who developed those programs are retiring. They have either retired or they will retire in a very short amount of time. So the state is now running short on people who can maintain and transition that kind of program to newer platforms. They have a shortage. They want people. So the reason why I'm mentioning this is because, excuse me. That's my Ring doorbell. So someone is delivering something probably. I do have someone at home, so I don't have to answer the door. But I could have answered the door from here. It's like, you can just drop the package as if I'm inside the house. So anyway, but because of that shortage, the state government actually wants to partner with ARC and other regional community colleges to train people to get into what they call mainframe programming. And once you get into the state, as an employee, you can transition, from one department to another department. If this is not what you want to do, you can move to some other place where the other place is doing something that you like to do. So I just want to kind of bring this up because I think in fall 2019, ARC might have certain partnerships with the state government, like the Franchise Tax Board and IBM itself, to kind of bring mainframe programming at least to the design hub, if not, as a class here. So we will have opportunities for students to kind of experience, what mainframe programming is about, and they have free classes too. So that's the other cool part. Yes.
That's like, would it be C++ language or would it be its own separate language?
Okay, so they program things in a variety of programming languages. At a shell level, they use JCL or Job Control Language, which is a really old archaic language, but there's still jobs specified using that language. So you have to learn it if you want to work for the state. Some programs are written entirely in mainframe assembly language, which is very difficult to read. And that's why, if you know how to read that assembly language and translate those programs into a more modern programming language like Java, you have just, secured your job, because there are very few people who can do that. So they do program in Java as well. The newer platforms, they use more modern programming languages like Java. So they have, and also COBOL. They have a lot of programs that are still written in COBOL, but they cannot be left alone. Because when our legislature changes, when the law changes, then they have to update the programs to reflect the change of the law. So they cannot just let old programs, sit around, just go like, we'll just keep doing it the same way as before, because the logic has changed. But they cannot afford to transition everything to Java or C++ all at the same time, because it's a huge, code base to transition. So we can talk more about this in future lectures, but I just want to give you guys an exposure to potential jobs in mainframe programming.